The transformation matrix. Now, if I have any linear coordinate transformation of a vector, I can always write the primed components as a transformation matrix Aij Vj. So this is going to give me a summation over J, and it's going to give me the ith component of the primed system. And now, how do I determine this transformation matrix? I can determine it from the basis vectors. If the vector v is written as vk ek hat, which is equal to vi prime ei prime hat, I can recall that vi prime is obtained by a transformation matrix aij vj. Now this vector v is vk ek hat, which is equal to aij vj ei prime hat. Okay. Now if I take, because this is now the primed components, v prime, so this would be equal to vi prime ei prime hat. This is vi prime ei prime hat. Okay, so if I take this vk ek hat dot product with ei prime hat, that would give me, I would have the dot product of ei prime with ei prime, that would give me vi prime. And I'm going to recall k as j, so this is going to be ei prime hat dot product with ej hat. The order doesn't matter here in the dot product. I called k to be j. It's now vj, and this is going to be equal to vi prime, which is aij vj. All right. So what I have done here is I've taken this equation and take the dot product with ei prime. When I take the dot product, ei prime dot product with ei prime, that gives me 1. So this is vi prime here. Here I have vk ek hat dot product with ei prime, or if I call k as j, it's vj ej hat dot product with ei prime, or ei prime dot product with ej hat, and this gives me vi prime, and vi prime is aij vj, as you know. So we can recognize our coordinate transformation matrix elements aij to be equal to ei prime hat dot product with ej hat, or I can say that aij matrix element is cosine of the angle between I prime and j basis vectors. So this is our transformation matrix. So the elements of the transformation matrix are the directional cosines between all the pairs of the basis vectors. So those are directional cosines. Okay, so we talked about how to find the transformation matrix so that we can write the primed elements of a vector, primed components, in terms of the unprimed components using a matrix multiplication. aijvj is vi prime. And this vector v can be written as vk ek hat in the unprimed system, or vi prime ei prime hat in the primed system. And the components vi prime are found to be Aij Vj. So that's what we have shown here in general. So it's a summation over J where we obtain the ith component of the primed vector. And if vector V is Vk Ek hat, and that's also equal to Vi prime Ei prime hat, where Vi prime is Aij Vj Ei prime hat. If I take the dot product of this with Ei prime hat, Vk Ek hat dot Ei prime hat, for the right hand side, Ei prime hat dot product with Ei prime hat gives me 1, so it's Vi prime. If I recall K as J, it becomes, and I can change the order here, it doesn't matter in the dot product, Ei prime hat dot product with Ej hat Vj. And this is Aij Vj, that's giving us Vi prime, so the matrix elements are Ei hat prime dot product with Ej hat, or they are directional cosines, cosines of the angles between I prime and J, jth element of the primed and unprimed unit vectors. So for all pairs of the basis vectors, we find the directional cosines, and directional cosines give us the transformation matrix. That's exactly what we had here, cosine theta 0, cosine 90 minus theta 0, cosine theta 0, and cosine 90 plus theta 0. That gave us the matrix elements, the transformation matrix elements. Now we can see it more clearly from this derivation.